Hi everyone, this is the reflection video for our 10th POGIL exercise. This exercise dealt with buffers, and we did it on October 9th and October 11th in class. This came from the second half of Chapter 8 in your textbook, and you'll notice that quite a big chunk of this chapter was devoted to buffers and the importance of buffers, and that just highlights how important they are in a lot of chemistry. So many equilibrium processes have a pH dependent component, particularly people who are interested in biological applications. As you know, enzyme efficiency and all sorts of other biological functions are really highly pH dependent. So it's really important that we are able to understand how buffers work and how to select and make a proper buffer for a proper application. So in this reflection video, I'm just going to talk a little bit about what we learned, and then also we're going to talk about buffer capacity. And buffer capacity is comes directly out of your textbook from page 177 on. So and that again will tell you not just how the buffer works, but how effective it works and how it will effectively neutralize the addition of acid or base in a system. Alright, so when we're talking about buffers, we spend a lot of time talking about the Henderson-Hasselbalch equation. So this is a really important equation to know. It's one of the most important equations that you end up using in a lot of equilibrium, and I suspect a number of you are taking biochemistry right now have seen this quite a bit already. And so what this talks about is how the pH of a solution is dependent on pKa of your buffer and the ratio of the base to acid form of your buffer in solution. Alright, and so we know that this is basically essentially how buffers work. As long as we are maintaining relatively close ratio of that acidic and basic form of your buffer compound, which is usually a weak acid or weak base, or you find it's a weak acid, weak base system. As long as those are pretty relatively close to each other, we can maintain a pH that's approximately around the pKa. I also want to say that, so this is an example of a buffer system where you have HA going to proton and its conjugate base. But buffers can also be set up in a different way, where your basic form is actually neutral, and then you add a proton to that, and then you get a charged cationic buffer species. So in this case, if you were to set up Henderson-Hasselbalch off of this, it would look exactly the same, but you have to make sure that you're always putting your basic form on top. Okay, so this occasion, you would have a Henderson-Hasselbalch that look like this. In this case, your basic form is uncharged, so you'd have your B here on top, and your protonated version, in this case, is cationic on the denominator. Okay, and so in order to know what range buffers are most effective, we're usually looking around the pKa. Okay, so I said that these are roughly when the acidic and basic forms are relatively close together. So generally we're looking at the pKa plus or minus 1 pH unit. Right, so that means, if you had a weak acid, weak base where the pKa was 7.0, that you generally want to be working in the range of 6 to 8.0. That buffer would be effective. What you're thinking about then is that basically you want your ratio of your base to acid to be somewhere between, so somewhere greater than 0.1 and less than 10. And that is, your buffer may work outside of this range, but the most effective range is within that ratio. And so we actually saw this. You guys did some of these examples in the POGIL exercise. So I want to bring up a topic that's from page 177 in your textbook, and it's fairly important. It's dealing with buffer capacity, and what this buffer capacity says is a way of describing how much change, or how much additional acid or base your buffer can handle without having a major impact on pH. So you see there's sort of two different forms of this. Both of these are, this D here, small d, you can think of it as the change in pH. And this is your change in concentration of, in this case, your base would be hydroxide. Right, and the same thing can be thought of in terms of your acid. So this here would just be your change in concentration of your proton concentration. Okay, so what this is telling you is that you can add a lot of acid here and have a very small change in pH. So that basically, as your buffer, you want is a large buffer capacity. So a large buffer capacity tells you that you can get either add a lot of acid or a lot of base and have a relatively small change in pH. So from your textbook, there's a picture that shows this graphically. So this is a pH buffer. You can see here. Here's sort of two plots of the same. Two plots here, and one of them is concentration of base added. So this would be like your hydroxide. This would be the pH change. And you can see there's this range here between what's about 4 and 6, where you can add quite a bit of pH of base, and you get relatively little change in the pH. And so if you want to think of this, basically, if you took the derivative of this plot, you would get your buffer capacity on the y-axis, and what you're looking for is where you get a maximum, right here, and you see that this buffer capacity maximizes around 5. So, and if you recall what we said, that the most effective place for your buffer to be behaving is around 5. So this, just looking at this graph, you can probably tell that this buffer probably has a pKa around 5, right? Because that's where it's most effective and it has the highest buffer capacity. And so buffer capacity is going to depend on the pH that you're using, so that's going to depend on the pKa, but it's also going to depend on the concentration of the species that you have. And so I'll show you what I mean by that with a couple of practice problems. So let's say that we have a couple of solutions here, and you see that these solutions are made of the same components, but different concentrations of them. And so this is the case we're dealing with carbonic acid and bicarbonate, and so this is a buffer system where we have, in this case, our carbonic acid is our HA, and our bicarbonate here is our A-, so it's the conjugate base. And so if you'll notice this, so we ask a question here, right? You have solution A has 0.1 molar of HA and 0.2 molar of the conjugate base. Solution B has 0.3 molar of the acid and 0.6 molar of the conjugate base. So the question is, which of these solutions has a higher pH? And hopefully you guys remember from the Henderson-Hasselbalch equation that the pH is dependent on the pKa plus the ratio, plus the log of the ratio of your conjugate base over the acid of your buffer. And we don't even need to know what the pKa's are for this to know that these are actually going to have the same pH, because if you see for solution A, right, our base over our acid is 2.2 molar to 0.1 molar. So that just equals 2. And so, and for our solution B, the same ratio is set up in this case. It's just 0.6 molar to 0.3 molar. And again, this equals 2. So in this case, the answer to this question, which one of these has a higher pH, this would be neither, because they both have the exact same pH. Because remember, your buffer is only dependent on the ratio. The pH is dependent on the ratio of these two, okay, not the total amount. But that's in stark contrast to buffer capacity, which we'll see in the next couple problems here. So the question is, all right, so which solution can neutralize 0.1 molar addition of protons? So if you add like a strong acid like hydrochloric acid. So if we look at this, if you look at solution A here, right, you can think about what we're really worried about is the ratio of your conjugate base to your acid. And so if we add 0.11 molar, we're just going to react, right? This is a strong acid, so it's just going to react with that base, a weak base here. And so what we're going to see is essentially this is going to be shifting our weak base by depleting it and adding it to our acid here. We're going to be shifting the equilibrium this way down here. And so if we want to set this up and think about this a little more quantitatively, we'd say we got 0.20 molar, which is our initial concentration of our base. It's going to be, we're going to be losing 0.11 molar of that. And we're going to be adding that to the denominator, which is our concentration of the conjugate acid. And so your ratio here is going to be that 0.09 to 0.21, okay? And you'll see that this is still within our buffer range. Remember I said that generally buffers are most effective in the 10 to 1 or 1 to 10 ratio. They'll still work beyond that, but they're most effective in this range. But what you don't want to see is to have either one of your conjugate acids or bases be completely consumed by the addition of an acid or base. So in this case, solution A can neutralize this. So we'll look at solution B, and you'll see that solution B can also neutralize it. And it's for the same, you just set it up the same way, but in this case, we got 0.6 on top, minus 0.11 as this base here is reacting with the acid, and it's forming more of the conjugate acid, which started at 0.3 molar, and now we add 0.111 molar, and so this ends up giving us that 0.49 over 0.41. Okay, so this is also going to neutralize it, and I'm willing to bet, I haven't done this calculation, but you can just see from these ratios that this ratio changed a lot more from its initial conditions. The solution A changed a lot more compared to solution B. If we went through the Henderson-Hasselbalch equation, we'd calculate that out, and I'm willing to bet that this would be a larger pH change than that. All right, so that gives you a little hint. By looking at these two, you can probably see that solution B has a higher buffer capacity, because remember we added more. We added the same amount of acid in this case, but we'll have a smaller change in pH from solution B. That means it has a higher buffer capacity. All right, so a follow-up question to that is, all right, what happens if we try to neutralize in this case instead of with 0.1 molar of the acid, but a 0.11 molar of the hydroxide? So we're going to start with solution B here. And you'll see that in case of solution B, right, this is just like we had before. We were talking about our ratio of our base to our acid. In this case, right, instead of reacting with the base to form acid, we're going to be reacting with the acid to form base. And so in this case, we're going to have on the denominator, we have our acid, which is 0.30 molar, and we're going to subtract 0.11 molar from that, and we're going to add that to the base. And so 0.11, this ends up being 0.71 over 0.19. You can see that, again, this falls within our range, and we haven't completely consumed either our acid or conjugate base. And so this buffer would still be working in that range. But if we turn our attention to the other solution A here, we'll see a different story. In solution A, right, if we set up exactly the same way, right, we put our conjugate base on top and our conjugate acid on bottom. In this case, we're subtracting 0.11 from the acid and adding it to the base. You can see here, just from setting this up, that we have more base reacting than we have acid around. So in this case, what you see here is that essentially this will not neutralize that, so this buffer fails. All right. So you're going to be out of the buffer zone. And so this is sort of a direct consequence of solution B. They're the same buffer components in the same ratio. Solution B has a higher buffer capacity, and so it does not fail when you add this much hydroxide, 0.11 molar. And so I sort of already said this, which one has the greater buffer capacity? In this case, the one that has the greater buffer capacity is solution B. All right, so we're going to follow up with one last question. We're actually going to calculate the buffer capacity to show you what I mean. And this is, if you want to sort of think about this more quantitatively. So in this case, we say we have a 25 milliliter solution of a buffer that has changed by 1 pH unit with the addition of a little over 4 milliliters of 0.35 molar sodium hydroxide. So again, we should recognize that sodium hydroxide is a strong base, right? So you're just adding hydroxide there that completely dissociates. And if we remember, our buffer capacity can be defined as the change in concentration of acid in this case, or base in this case. It's a ratio of that change in concentration over the change in pH. Okay. And so in this case, we already know our change of pH is given to us here. We change 1.0 pH units, so this is just 1. We have to figure out a change in concentration of hydroxide. And so this one is we can do our old friend, M1V1 equals M2V2. In this case, I'll just call it C1V1 equals C2V2. So our concentration at one volume equals the concentration times the other volume. And so in this case, we know we'll set up our M1V1. So we got our concentration that we added here is 0.350 molar times 4.06 milliliters, and that is equal to our we're trying to figure out what the concentration of adding that to this other buffer solution is, which is 25 milliliters. So all you have to do is divide both sides by 25 milliliters, multiply these two together, and you get your concentration 2, which in this case ends up equaling 0.0570 molar. All right. And so you'll see here that what we did was essentially convert from this and to so what we saw was that by changing the concentration by this much in our buffer solution, we changed the pH by 1. So the beta in this case is relatively simple because we can just plug our concentration here in the top. So that's 0.0570 molar divided by the amount of pH that's changed, which is 1.0. So this beta just equals 0.0570 moles per pH. Okay, so that is our buffer capacity. So that's how you sort of calculate it quantitatively. So hopefully you all can follow along, and if you want to find out some more information, again, that's in Chapter 8 on page 177. And so I'll see you guys in class on Monday.